So modern atomic theory is the idea that all matter is composed of atoms. It grew out of different observations and laws, specifically these three: the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So we're going to look at those different laws. Remember, a law says what happens, and a theory explains why. So atomic theory is explaining these laws, these observations that have been made. So the law of conservation of mass can be stated as this. In a chemical reaction, matter is neither created nor destroyed. And we mentioned Antoine Lavoisier in the first chapter. He's the one who really came up with this concept in 1789. So he was the guy who was burning things in closed containers. And he found that if you measured the mass of the contents before and after burning it, the mass was the same. And so his idea was the total mass, all the mass you start with is all the mass you end up with, and you can't make or destroy mass. So in a chemical reaction, the total mass of stuff doesn't change. Relate this to Legos again. If you make a Lego creation and you put it on a scale and you see how much it weighs, and then you take those pieces apart and you make something else using all the same pieces, is it going to weigh more or less or the same as the first structure? It's going to weigh the same. It's got the same pieces in it, right? So what atomic theory is explaining is that in a chemical reaction, the particles just get rearranged like the Lego bricks get rearranged when you build something else. The individual pieces, the individual atoms are all still there, and so the mass can't change. Matter is conserved. The particles themselves are indestructible. We can look at reactions like this. Here we've got sodium, the element. It's a metal. It's soft and shiny. And it looks like a metal, but you can cut it with a butter knife, so that's kind of weird. And then here's chlorine gas. So here we have an illustration of what the particles look like. And when those two substances react, they form sodium chloride, which is table salt. If you put 7.7 grams of sodium and 11.9 grams of chlorine, and you react those together, the mass of the product that you get is the same as the sum of the reactants. You're not making any matter, you're not destroying any matter. Because all you're doing is you're taking these little spheres, they look like marbles, don't they? And you're putting them together in a different way. Okay, conservation of mass. Definite proportions. Another French chemist, Joseph Proust, made observations about the composition of compounds. And so his observations are known as the law of definite proportions. All samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So let's think about water. If you take 18 grams of water and you decompose it into hydrogen and oxygen, you see that the ratio is 16 grams of oxygen to 2 grams of hydrogen. The mass ratio is 8 mass units of oxygen to 1 mass unit of hydrogen. It doesn't matter where you got that water from, whether you made it in a lab, whether you collected it from the Kings River, got it from a cloud high in the atmosphere, took it from the Nile River, the Atlantic Ocean, doesn't matter. All water is composed of the same two elements, and their proportions are constant. Okay? So we should be able to do questions like this. And this is not a super important type of problem, but it's actually pretty simple, but it messes people up because you guys have had chemistry before, and so you know about stoichiometry and stuff like that, even if you've kind of repressed that because it didn't make much sense, you've heard about it. So you have to set all of that aside when you do a problem involving definite proportions. So let's look at this. Two samples of carbon monoxide are decomposed into their constituent elements. One sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So, definite proportion says that the mass of one element to the mass of the other element for a compound has to be the same for all samples of that compound. So here we've got two samples of carbon monoxide, and we're given masses. So there's 17.2 grams of oxygen and 12.9 grams of carbon in the first sample. So we could calculate the ratio. I always like it when you put the larger number on top because that gives you larger numbers. I forgot my calculator. So 17.2 divided by 12.9. So that gives me 1.33 repeating. Are these exact numbers? Masses of oxygen and carbon? No. These are measurements, and we assume that there's uncertainty in the last digit. And so we'll use the rules of significant figures, and the calculator is showing us this. But each of these numbers has three significant figures, and so dividing them, we should still have three significant figures, and that's going to give us 1.33 gram. No, not grams. There's no unit on that. It's a ratio. So that's oxygen to carbon for the first sample. Then we're going to do the same thing for the second sample. The second sample wasn't as large. That's why there's not as much oxygen in it. But the ratio should still be the same according to the law of definite proportions. So we can take 10.5 grams of oxygen to 7.88 grams of carbon and see what that gives us. Okay, my calculator is showing 1.33, 2, 4, and then it goes on. But I can tell by looking at my starting numbers that this should have three significant figures. So I don't need to, I'll write down two extras, but I don't need to write down all the rest of them. And then when I round that, I get 1.33 again as the ratio. Is this consistent with the law of definite proportions? Yeah, it is. The mass of oxygen to the mass of carbon is the same for different samples of carbon monoxide. Any questions? So law of multiple proportions, that just on the surface seems to contradict, right? Law of definite proportions, law of multiple proportions, which is it? So John Dalton's responsible for this one again. Law of multiple proportions, it's a little hard to express. So we'll read it and then I'll try to explain it. So when two elements, and we're just going to call them A and B, when two elements form two different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. So that probably doesn't mean a lot. Breaking this down, one atom of A can combine with one atom of B. So we could have a formula where we've got one A and one B, or maybe it will form a compound with 2 atoms of B or 3 atoms of B. These are individual particles, and just like Lego bricks, you can have one red one and one blue one, or you could have one red one and 3 blue ones, but you can't have one red one and 1.5 blue ones, right? Those ratios, the masses of B that combine with A are going to be in fixed, I hate this explanation, small whole number ratios. Okay, let's look at this. Carbon monoxide, carbon dioxide. Two different compounds composed of carbon and oxygen, right? So in carbon dioxide, the mass ratio of oxygen to carbon is 2.67 to 1. So in that previous example, we looked at, we had the ratio of 1.33, and that's this one, 1.33 to 1 mass of oxygen to carbon. So a ratio of 1.33 to 1 says that there will be 1.33 grams of oxygen for every gram of carbon. And this ratio says 2.67 grams of oxygen for every 1 gram of carbon. Multiple proportion says if we take the ratio of the ratios, we should get a small whole number. So 2.67 divided by 1.33, what's that give us? So my calculator is showing 2.0075. It's a ratio of 2. That tells us in this compound, for every carbon, there's twice as much oxygen. Because it's particles, it has to be whole number ratios. And these guys observed these laws before they knew for sure that there were particles. So here we've got carbon dioxide. We know that it's 1 carbon and 2 oxygens. They didn't know that. But the mass of oxygen that combines with 1 gram of carbon, 2.67 grams. Carbon monoxide, 1 carbon, 1 oxygen. Here's the ratio. We take those two masses, and that gives us a ratio that is a small whole number. It has to be a small whole number. That number is the same as the number of atoms of oxygen here to the number of oxygen atoms in the second one. Any questions? That was definitely not my best explanation. So, example problem. Hydrogen and oxygen form both water and hydrogen peroxide. Decomposition of a sample of water forms 0.125 grams of hydrogen for every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 0.25 grams of hydrogen for every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. So we have two different compounds here. Law of definite proportions applies to a single compound. Law of multiple proportions, we're looking at different compounds made out of the same elements. So the water is 0.125 grams of hydrogen to 1 gram of oxygen. And the hydrogen peroxide is 0.250 grams of hydrogen to 1 gram of oxygen. So the law of multiple proportions says that if we take the ratio of these two numbers, that should be a small whole number. So take the larger one and divide by the smaller. And ta-da, we get 2. Could be, you might end up with 3 or 4 or something, but small whole numbers. Any questions? So those are the laws. John Dalton's atomic theory explains those laws. So each element is composed of tiny indestructible particles called atoms. That's an explanation because that cannot be directly observed. Atoms of a given element have the same mass and other properties that make them different from atoms of other elements. The atoms combine in simple whole number ratios to make compounds. And atoms of one element cannot change into atoms of another element. In a chemical reaction, the only thing that changes is how the atoms are connected to each other. The individual atoms are not changed. I will not ask you to write out a list of what is Dalton's atomic theory. But you should understand these concepts that are found in it.